I think I'll just give a brief introduction about myself. So obviously the Apple II is not my day job. Okay. So my day job, I work as an embedded security researcher. So I work at this organization called CSIT, which is under MINDEF, Ministry of Defense. So what I do is actually I deal mostly with PCB hardware design, microcontroller firmware, as well as embedded Linux, which is should be different compared to most of you here. Okay. So okay, so let me just go straight to the top. So my talk was actually my work was actually featured by Apple's Swift blog. So you can read over there. Yeah. So I basically brought Swift to the Apple II. So most of the time you think of Swift, you think about Apple's latest MacBooks or iPhones, right? But what about Apple's earliest product? Okay, so I need to give you all a brief history of Apple's very early products. So the very first Apple product, right, is called the Apple I in 1976. I don't need to introduce to you who are these two guys. I'm sure you all know who they are. Okay, so this Apple I, you can see in the photo, it runs on the 1 megahertz MOS 6502 CPU. You can look at the RAM, it's in single digit kilobytes. Okay, the storage is not a hard disk, it's a cassette over there. Okay, then designed by Steve Wozniak, only 200 units were produced at that time. As of today, 60 to 80 still exist, only 20 is working, still working. Yeah, so you can look at today's price, inflation adjusted. It's quite costly. If you want to try to buy one today, prepare to have $1 million US. So that's why I don't have one. Okay, so now let's go to the Apple II. Okay, so Apple II is what people will consider as Apple's first mass production consumer product. Because obviously the Apple I, 200 units, you wouldn't consider it as a mass consumer product. So Apple II, a mass consumer product, about a couple of million of them were produced throughout their entire lifetime. So the first Apple II was released in 1977 using the same MOS 6502 CPU, same amount of RAM, with a 256 byte ROM, with this cassette storage. Okay, so it has something, it runs with a programming language called integer basic. Okay, it's not like what we have like C or Swift today. Okay, then there was a small iteration released 2 years later. It's called the Apple II Plus, which is what I have here. Okay, just a small iteration. They bump up the RAM. Okay, it has something called AppleSoft Basics, which actually Microsoft wrote it. Okay, it has a feature called Auto Start ROM. Okay, so basically now this Apple machine can automatically start from a floppy drive. That's a feature on its own. Okay, then Apple IIe released in 1983. It's called enhanced version. So Apple IIe came with support for uppercase and lowercase characters. Or you take it for granted today. That was a feature. The Apple II Plus can only do uppercase characters. And then there's a full ASCII keyboard. Okay, this Apple II Plus does not have a full ASCII keyboard. Later I'll show you, there's some issue about this. Then 64 kilobytes. Oh, sounds very big, right? Number, right? Today very small number, but that's a big number at that time. Okay. So to reduce cost, they reduce the chip count. They combine certain chips. So to reduce cost. And they support an optional 80 column auxiliary card. So basically your text can now be 80 columns. Before that was 40 columns. Okay, later Apple IIs, 1980s. Okay, so Apple IIc, they shrink down. They call it compact. Okay, you see these three guys? Yeah, very famous guys. Okay, so now he has 80 column card, floppy controller. That's a feature on its own. So it officially support a floppy drive. Okay, serial port and mouse port. Then Apple II GS. GS stands for graphics and sound. Okay, so it uses a faster CPU. It can still emulate the original Apple II because they have a lot of software. They need to maintain the continuity, and it has more RAM. Okay, so the sound is provided by wavetable 66 chip. So one of the final Apple IIs, right, was in called Apple IIc Plus in 1988. Okay, so they increased the CPU speed. They had support 3.5-inch floppy drive. Okay, so how is this famous at that time? Okay, so in 1977, there's this term called the 1977 Trinity. So it's these three famous PCs at that time, where Apple II is one of them. Okay, you can see computers at that time, it was not standard shapes. Very unique. Okay, so for a user of Apple II Plus at that time, how did it feel like? Okay, so the Apple II Plus, right, is an integrated keyboard. You can see over here. Today, most of our keyboards, right, at least on the desktop machines, your keyboard is a separate piece on its own, right? But at that time, the computer systems, the form factor was not that standardized. So they copied the typewriter type of layout. Okay, Then the output is through a composite video output, because at that time there was no such thing as HDMI or DVI or even VGA, not yet. So the typical TVs they support a composite video. So the computers also output composite video. Then they have joystick. Okay. There was also a floppy disk drive. You can see over there. It's a 5.25 inch, 140 kilobytes. Yeah. Today is it's like a spec. Yeah, but at the time it's a lot. Okay. So what about the operating system and the firmware at that time? So by default, the machine comes with AppleSoft Basic, which was written by Microsoft, okay, because they didn't have time to do it, so they took from there. Okay, then there's another operating system called Apple DOS 3.3, which was the first one. Then there's another more professional version called Apple DOS 8, which was released sometime later lah. Okay, so I'll come to my project, which is called, I call it Swift 2. So what is Swift 2? So it's a mini Swift development environment. It comes with REPL, it comes with a microcompiler, it comes with a virtual machine, text editor, file manager, all to run on the Apple II. Okay, so goal of a Swift 2 is that I want to build a Swift subset. The version of Swift that still can run. It looks like Swift. Obviously, it cannot be all of the Swift that we know today. It's impossible. Okay, then I want it to start from a floppy disk, the 140K 5.25 inch, to replicate what a user of that time would feel when they use the machine. Okay, so for that, right, the operating system I'm using is called ProTools 243. Okay, it's a modern remake of ProTools. Okay, then inside the disk I will have the Swift 2 binaries as well as sample programs, and obviously I have to develop with AI assistance, which is now expected today already. Okay, so for this, right, I will first begin with a quick demo of the REPL. Okay, so let me do it. Okay, so now let me turn on the machine. So I've streamed the video in. I hope the demo gods will be with me today. This is almost a half a century old machine already.
Where did you get it?
Someone donated to me. Of course, I had to fix it first. When it was donated to me, it was not fully working. Okay, so you can see on start, right? I have a mini text-based user interface over there where you can decide what you want. You see, I can just select. Okay, so for now, I want to show you the REPL. Okay, so let me press enter for it. So now it will load the binary. Okay, so right now it's loading from this floppy disk emulator because I don't have that drive. Okay, so I have this thing here. Okay, so now this is the REPL. Let me type some very simple Swift code. We don't have a lot of time, so let me type some. So I just do this. So I let result equals 40 plus 2. Okay, enter. Okay, so now I print the result. Sorry. Okay. Enter. 42. Okay. Very simple, right? Okay, now I do a for loop now. Okay.
So is it maximum 80 character per line?
This one is 40 because I didn't enable the 80 column mode. Okay, I'll come to that in a while in the presentation. Okay, so I will do this. Okay, so let's do this. Okay, I'll explain to you later why this special syntax. Why is that bigger than sign with the percent? See, it's not that user friendly to type. Because we are used to the keyboard being low to the table, right? This one is a bit high.
Maybe you can ask someone to type it for you.
Okay, so we have a simple for loop there. Okay, so now, right, this is the REPL mode. I will show to you the compiler mode. Wait, let me. Okay, so for that, right, I will use emulator because rebooting will take some time. So I'll use the emulator here. Okay, so I select a file. Okay, so you can see, right, these are the volumes, the disk volumes. So this is one floppy drive, this is another floppy drive. Okay, so let me run a sample. Okay, so I have a snake game over here. Yeah, let me see. Okay, so you can see the user interface of the file manager. Here is the parent directory, here's the current directory, and here's the preview panel. Okay, so in the preview panel, right, you can notice that I can scroll as well. You can preview the Swift code here. Okay, so now let me run this code. So right now I will first compile this Swift code. Okay, gives us some. This is full. Okay, let me delete something. Oh, never mind, I just run it here. It's okay. This is a demo god not with me today. Let me delete this one. Delete away. Delete away. Wait, let me come here. Okay, so now I can select the speed. Let me select speed 8. See, so I have a snake game here. Can see this. Okay, let me just crash into the wall. Done. So we have a mini game written in Swift running on here. Okay, so let me continue. Okay, so before I can go to the software, right, I need to first talk about the hardware expansion cards that I have to install in this system, because the hardware will greatly influence how I wrote the software. Okay, so the expansion card that I have on here is called the Satan Rocket. It's basically a 128K expansion card on here. Okay, so this is what this is a larger alternative to Apple II 16K language card. So at that time, right, Apple supported language called BASIC as well as assembly code. So those two are a bit too extreme. BASIC is basically like the Python of today lah. Then assembly code, is very not approachable for beginners. So you have these two extreme. So they decided to have Pascal. Pascal is like the Python of today. Yeah. Okay. So but the problem is Pascal, they needed more memory. So when they released Pascal, they released something called 16K language card. But it's a bit hard to get a 16K language card today. So I got the Apple II System Rocket instead. Which can emulate the language card as well as have more memory. Okay. I have this machine by default only supports 40 columns, so I bought a expansion card lah. So the machine can support 80 columns. Yeah, you can see the difference lah. This is 40 column. You can see the 80 column mode. The text width is smaller. Okay, another one I got was also the disk controller card. So Steve Wozniak at that time he designed these two interface card which is what you see on the bottom left. Okay, it's because at the time people complain you use a cassette. Cassette is very slow. So they invented this floppy disk connector this card, which is designed to talk to the disk controller. But I don't have both of these, so I got the more modern alternative. So this floppy emulator reads the disk image from a SD card. Okay, so the motivation why I decided to embark on this project. First, this machine was donated to me. So the first thought was, after fixing up this machine, right, like what modern features can I attempt to put on this machine? So I thought, why not try to bring Swift to this old Apple device, like one big circle back, okay? And also to try using modern AI assistants to help me, because this project, to write interpreted compiler, even in modern times, is not easy thing to do, much less on a machine that is like almost 50 years ago, right? Okay, so now I go deeper. The first thing before you write any program, you need to know the constraints that you're working under. So this machine doesn't have a lot of RAM. Okay, so this is what we call a 40,704 bytes barrier. Okay, so on the Apple II, right, you can see that the maximum amount of RAM that it can address is 64K. This is the entire memory map. Okay, from 0 to FFFF. Okay, or the main RAM, right, 48K, right, is only up to BFFF. Okay, out of that, right, okay, up to here, out of that, right, some of it is already used by the operating system. So like this part is used for input output addresses. Then ProDOS is the operating system, already eat up some, and ProDOS will load your application to this memory address of 2000. Okay, so in effect, right, the amount of memory that your application can use is slightly over 40K, which is this range over here. Okay, so what about expansion cards? So I mentioned about I have a Satan Rocket inside. So and the Apple II language card. So Apple II language card, right, they use the upper range, the memory. Okay, but the problem is this upper range is shared by a lot of stuff like the model ROM, then all the banks are. So it's a bit of a challenge which I'll go through. How did this work? Okay, then this Apple II so 128K Satan bank card, right? How do they fit inside this smaller range, only 16K? Because they do something called memory banking. So basically, you have a lot of memory, but not all can be accessed at any one time. Yeah, this is something that machines of that time period, 1970s and 80s, they do that. Modern machines no more do this already. It's all flat memory space. Okay, then on Apple IIe, there's another difference. They support a 64K auxiliary memory card. Okay, so this one operates differently. This one operates like a bank within the main memory itself. So the Satan card, right, the bank memory is on the upper memory area. But on the Apple IIe auxiliary RAM, is the bank is within the main memory itself, which is a different way. It's a extra complication. Okay. What about development environment? So to compile this project, right, I use CC65. So CC65 is a program that is still run on your modern Mac. It can compile code to target for 6502 CPU. Okay, it can compile C code, it compile assembly code. So how did I develop this is that I use this CC65 to compile code to target Apple II, but I still have Clang to run my unit tests. So because it's C code, right, that means C code can work for both the 6502 compiler as well as work for Clang. Okay, the language I use is C90. Okay, so in theory I could have done with assembly lah, but then I'd rather not to because it'll be very hard to debug this Okay, emulators I use Isaac Apple II and Mariani. So just now you all saw the emulator, that was Mariani. Okay, because when you develop software, I don't want to keep porting it the software to check. Basically you develop first, everything is done on the local emulator first, then occasionally you go and check, make sure it actually works on the real hardware. Okay, so what about architecture? So in this is architecture that I use a compiler runner architecture. Okay, this is actually very similar to how Java works. Okay, so you first start off with a Swift code. Okay, then Swift code you pass it through a lexer, or what we call a tokenizer. Then after that you send it through a compilation process. The output is a bytecode, and this bytecode is run by a virtual machine. Okay, so this entire chain, yeah, obviously is running on my Apple II. Okay, so this way of handling code, right, is actually inspired by the Apple Pascal and Java. Apple Pascal in 1979 already did this architecture already. So if it worked then, it definitely can work today. Okay, I did thought of why not write direct compiler direct to 6502 assembly. Then I think it's a bit difficult because definitely way more difficult. The compiler will probably not be able to fit inside this Apple II. Okay, I also have the REPL. So just now you all saw the REPL, right? The REPL is a computation of everything, right? Yeah. So but then once you have everything means that you have lesser features. So there are certain Swift functions not available in REPL. Okay, so how does my version of Swift compare to the actual Swift? Okay, so the actual Swift, right, for example, the integer is usually 64-bit sign, right? I cannot have 64-bit sign, so I use 16-bit sign only. Okay, and I don't support the floating point. Okay, string in Swift is a collection of Unicode character types. I cannot support that. So I resort to ASCII array, which is actually what C does. C is ASCII array for string. Okay, then for array, Swift you can put multiple types, right? Cannot, it's too difficult for me. I just all items the same type. Okay, identifier length, basically your variable length. I checked online, right? It seems that Swift does not have an upper bound. Yeah, it seems like it's like I cannot find a limit. So but then for me I kept to 11 characters again to save the memory space. Okay, so why no floating point? Because the CPU does not support it. Okay, so the 6502 CPU has no floating point in it. Okay, and therefore the compiler also does not support it. So the alternative, if you really want to have float, right, you need to have a software library. Okay, now the problem, if you do a software floating point library, it will not be fast for sure. It will be very slow. Okay, then you eat up definitely more disk space and memory. Okay, so I actually asked AI to help me to do this. Then it actually took about 3 kilobytes of memory, which is a lot for this system. So I tell AI, I just drop it. No point. Okay, so what kind of other Swift language I support? So the basic letvar, okay, the branching if else, short circuit boolean, top level functions with return. I say top level function means no nested functions. I don't have the memory to have nested functions. Okay, then optionals, okay, I have with arrays and string concatenation. Okay, that is for the core. If the system has more memory, let's say you have the Satan card or the auxiliary card, then I'll add in integer parsing, array methods, as well as Apple II graphics. So these Apple II graphics are GR, color, plot, H line, V line. This is Apple II specific thing. It's not a Swift thing. Okay. Then let's say if you have a compiler runner setup, then I'll support even more. I have a switch, I for in, I random, okay, and then speaker and file IO. Okay, so features not supported. Yeah, these are very, very complicated features. So I cannot. Okay, so how modern compilers work and how, because I need to explain to you how modern ones work before you can understand why I did what I did. Okay, so a typical modern compiler, this is for Swift, right? So when you pass Swift code through the compiler, what's the first thing you have to do? Is to do a parsing, right? Basically something like tokenizing. Then it needs to create an abstract syntax tree like this. So this abstract syntax tree basically decides the ordering of the code. Okay, then this AST, right, is sent to something called Swift, to make something called Swift Intermediate Language for optimization. Then this seal, right, is sent to the LLVM to make a Swift IR, intermediate representation. Then after that, Swift, then LLVM IR will be sent to LLVM backend to generate the binary that is specific to your CPU. Okay, so this is the typical way how it works. Okay, so on my system, right, I cannot do this way because this AST, right, is actually a very memory heavy thing. It definitely has to be as big as your source code, definitely bigger. So I cannot hold it. So what I decided to do, right, is do something called a single pass compiler. That means as the compiler reads the source code, it will generate the bytecode on the spot. It will not create this entire big AST, then generate. No, it see, read, generate. Okay? Then definitely no complex features optimizations, because certain complex features, right, require to have a wider view of the source code, a wider window. Okay, so I can't do that. Okay? So that's why I don't have things like the like closures, for example. Okay, so a sample, how do we compile source code? Let's say you see this. Let x equals 1 plus 2, then print x. How does it work? So the first thing is called lexer or tokenization. You need to extract out the key parts of this source code. Okay, so to identify what they are. After that, right, the compiler will push them into a stack in something called precedence order. Okay, so you can see that to pass this, I push the number 1 and number 2. Then for the add function, I'll pop the two of them, do the operation, and push back the sum. Okay, then after that, I will assign it to a global variable, so bind to x and then push x back. Then when it comes to printing it, right, okay, so printing, I have assigned an opcode to it. So when the runner sees this opcode, right, CV63 in this case, it knows that, okay, now is the time to print it. Okay, so this is just a sample bytecode. Okay, for distribution, so I distribute in 9 disks. If you wonder why so many, okay, it's because I have 4 disks for the REPL and 4 disks for the compiler runner. So each of these 4, right, is to target a different hardware configuration. You can see 2 plus with Satan card, 2E and 2E with the auxiliary card. Okay, because each way of doing, right, each of these hardware, right, requires a different way of handling, and I cannot squeeze all into one disk. It's very hard to decide to detect the machine also, which one is which. Okay, so what's the difference between all of them? So the REPL one, right, it compiles the bytecode in memory and run it on the spot, right, so that you are able to give you the code. Okay, so because of that, I have lesser Swift features, and also I want to eat more memory, so I have to eat into the ProDOS, the operating system's own memory. So the part that I eat into is something called the machine language interface. So basically the part of the operating system where does file IO, your read and write files. So I don't space I eat into that section, but because of once I eat into that section, right, you can no longer read and write files already. Okay, but it doesn't matter, this REPL, it doesn't need to read and write files. But the problem is for the compiler runner, right, it needs to read and write files. So I cannot just override the operating system. Okay, so but also because it's split into 2 binaries, compiler runner can support more features also. Okay, so extra memory. So for Satan one, right, is occupies this space, so I can execute code in place. But the problem with the auxiliary RAM, right, I cannot execute code in place. I need to first copy out the contents of the auxiliary memory into a staging buffer, then run in chunks by chunks by chunks. So that is actually a very challenging thing for these two ways. On paper they look like same amount of RAM, but in practice to handle this is very difficult. Yeah. Okay, so now I have come to another challenge. What you type versus what you see versus what you store. Today we take it for granted that everything is the same, right? What you type on the keyboard and what you see on the screen and what the computer says to this. Everything's supposed to be the same, right? It wouldn't occur to you there's something different, right? Okay, on Apple II, there's a difference. So on the Apple II Plus, right? Remember I said it cannot support lowercase. Okay? And it does not have the full ASCII layout. So it does not have the braces. It does not have the square brackets. It does not have the slash and the tilde. Okay? And it does not have the up and down arrow keys. You notice? This is the left and right. Okay? It doesn't have up down. Then on the Apple IIe keyboard, this one is more standard. It has both upper and lower case, complete ASCII, up, down, left, right, but all in a single row. Okay, so if I were to target the Apple IIe, it would be easier because Apple IIe is more closer to what we use in modern times. But Apple II Plus, that's a challenging thing. Okay, so how do I get around this? So there's this concept called digraph and trigraph. Okay, you all may not heard of it. So it's a very old concept. Basically, is you use 2 or 3 typable or typical characters to represent one character. Okay, so the standard I follow is called the C standard. I mean, C language is quite old, so it was designed at a time where this could be an issue. So they have a standard that says that, okay, if you cannot type certain character, what are the characters that you can type in place of that? Okay, so you can see that some of the examples here. The canonical Swift, what I decide to store is basically the actual one, the canonical Swift, which is it can support the full ASCII, right? But what you type, you can see that, for example, the square brackets, right? I will type this. The slash, I will type this. Then the braces, I will type this, and the integer, right? Yeah, like that. Because I cannot type lowercase, okay? Then on the screen, right, some characters can be shown. Like the square brackets can actually be shown on the screen. It's just it cannot be typed in, okay? So what I had to do is that I have a translation layer. So whenever the runner sees that, or this one, right, and the screen cannot display, right, you automatically replace the characters to show that in a way that it can be shown to the screen. Okay, then the next thing is development environment. Most of us, we take for granted that everything is provided by the OS, right? So when you write interpreter or compiler, right, in practice, right, I cannot just provide that, because how can a person use it then? You need to have a launcher, you need a file browser, you need a text editor. That's what most people will typically think of before you will consider a development environment to be complete. Okay, so I have all this in one binary. So the file browser I showed you all earlier, right? It has a parent directory, current directory, and preview. Then the preview also, it has a 1.5 second delay I put in. Okay, because you don't want it to straight away read from the disk. Remember, the floppy disk on this is very slow to read. So unless the user has hovered the cursor there for 1.5 seconds, then I'll read it. If not, I don't read it. Okay, and this one also, yeah, you see the preview pane. Text editor. So a modern text editor, what do we expect? You want to have something line numbers, right? Obvious, right? You want to have a cursor position, keyboard shortcut, and to know whether the file has been saved or not. Okay, so I provide all of this. You can see the line number, the cursor position, as well as whether saved or not. Okay, then there are 2 modes. Okay, so what I call the cook mode, the raw mode. Okay, so why they exist? Because remember, the Apple II Plus cannot show certain characters. Okay, so I need to convert them in the way that the characters can be shown. Okay, you can see this example here. Okay, but on the newer Apple machines, they can be shown. So I need to show as raw mode. And this text editor also have to save the file as canonical Swift, the actual lowercase and all, so that it can be compatible with all the others. Then what about up and down? Remember, this one has no up and down arrow. Only got left and right. So I use Control O and Control L. I follow the Pascal standard. Display outputs. So this one is a more quite a complicated thing. So 40 column, 80 column, different column size. And then on Apple II and Apple II Plus, I need to go through a translation layer because they cannot show certain characters. But on Apple IIe onwards, they can show the characters. So it need to be treated differently. Okay, automated testing harness. So I wanted a way for me to check, because remember there's so many different hardware configurations. If I make a change, can I be sure that this change can work? Or open, or you know how to launch one emulator at a time to check very, very difficult. Okay, so I show you a quick video on the automated test harness. So you can see I asked the AI to generate from this is actually a web page. You can see that what it does is that you automatically boot up the different versions, issue keyboard shortcut the keyboard commands. After that, right, it will script the screen. For every screen change, right, it will script and check whether this is the expected output. And you run it through all the combinations. You can see all the different software combinations against all the hardware combinations. Yeah, so to be sure that it works. You can see it's automatic. Okay, so AI development tools, everyone very into this now. So I use AI for this, definitely. So at that time, it was Opus 4.8. So I use Opus 4.8 for planning and coding. Then I use GPT 5.5 to review. So you have two AIs. Then given the project complexity, I cannot single shot it. You can see really, it's too complicated. It cannot be done in one single prompt, just everything out. So cannot. Then I developed in 2 months on the side only, Yeah. Okay, so this is the process. So I got AI to draft me the initial agents.md. After that, then I have durable documents. Because LN context window is very small. So I need to have documents to decide this certain feature, how can it be done. So I divide my project into 18 phases. You can see from the scaffolding REPL function into 18 phases, and there are 20 design documents. Every design document represents a feature that I want to develop. So what I do is that I create a draft design document. I iterate with the AI first until I get to the point that I like this is how it's done. Then I tell the AI, okay, generate the code for this. Okay, I come to the end. Okay, last slide. So one circle, right? So for modern Swift, Apple created Swift, I think released in 2014. Then now Swift is back to the first mass market machine. Okay, with this project, right? If you ask me to do it just like 1 year ago, I would say it's almost impossible. Unless you have a lot of time. If you want to do by hand, I think take 2 to 3 years. Yeah, you can see the complexity of this. Then thanks to these people, Steve Wozniak. Most people think of Steve Jobs, they forgot about Steve Wozniak. So Steve Wozniak designed the machine. He designed the open architecture, the slot type, and the entire machine is actually open source. You can still find the schematics. If you want to build an Apple II today, you still can. Okay. I read a book called Crafting Interpreters. Right. So even though technically AI did all the coding, but you need to know how to prompt it and what are the terms to use. So this is what I find. So when I do a project nowadays, I try to get some domain knowledge. So I got domain knowledge from this book. So I know how to prompt the AI in a way to generate in the right code, and I can know whether AI is actually generating the right code also. Okay. I like the emulator creators, Isaac Apple II and Mariani, without which cannot. I cannot be possibly generating the binary and then just trying every single time. So I can do the fast iteration of my machine. Okay. If you want to try this project, you can. I already open source everything already. Just download this image. You can download the emulator Mariani, like I showed you. You all can try. Yeah, that's all. Thanks. Okay. If you all have time for question, if not, yes.
Do you have the source code on GitHub or?
Yeah, it's on GitHub.
Can you share the link to that?
Yeah, the link is on my first. Like you can just search for Swift 2. Swift II. Just search for that link. You can find.
Do you have the link for the slides?
Sorry?
The slides that you presented. Do you have the link for this? The PPT.
Oh, I tell you what, I think I can upload it to my. I have a blog post on this. My slides are actually based on the blog post. You can read from it. Yes.
Out of the 2-3 months development time, how much time you allocate for the design PRD? How much time you allocate for
Oh, okay.
the later loops and then debugging?
Okay, the PRD, okay, the documents I would say, right, I think it's about half. Because once you have the PRD up, right, generating the code is the easy part.
Easy, like one hour can finish?
Okay, how I put it? I did over 2 months, mostly over the weekends and weekends. So definitely it's not a 1 hour thing. Because, okay, when I generated the documents, it's not a one iteration thing. So actually when I generated code, then I see that actually certain things, right, not enough memory. Then I need to trim or adjust the PRD. It's not like I create one PRD, straight away go to the code and that's it. Yeah, so a lot of hours spent.
How many rounds of deployment on the virtual machine?
I cannot count. Too many.
More than 100.
Well, definitely more than that. Remember, I got so many hardware combinations alone. I have the 2E, the 2E, 2 plus, 2E, that each one got their own.
Already auto,
The auto did not come first. The auto came later.
Or the auto came later?
Later.
Before the auto is 100 iterations.
I had to do by hand first because only when the problem became okay. Initially, the problem wasn't that big. My target was actually a 2+. Then I thought that since AI is doing the code now, I'll spend more effort to get it working on 2E. So basically, the project grew to a point where the auto testing harness became needed. Initially, it wasn't that needed.
Wow.
Yeah. Oh yeah.
Did Opus write a parser and AST?
Yes. No, I didn't use no AST.
No AST?
No AST. I mentioned there's no memory for AST.
Oh, okay.
So it's just a parser, then a single pass compiler.
You write by hand, are you able to write
Probably can in a 2 year or 2 or 3 years. For the whole thing, I mean, not just the compiler. The compiler actually asked me, took about, I would say 20 to 30% effort. The remaining effort was actually the launcher, the editor, and all the compatibility checks. The testing was actually the long one. The compiler, once you get the logic right, is not that long actually. Yeah.
What's the inspirations of future applications for this time?
No future application, be upfront. Don't have. This is for fun.
This inspires you can write how much in a simple, one piece controller, right? Automated EEPROM. So now a lot of single piece controllers runs in your mobile, runs in your.
Okay. Well, my job as an embedded systems, I deal with this kind of low, they call constrained devices, where the device has not a lot of memory. Devices with like few kilobytes of RAM is something that I do actually.
It's a luxury.
I would say luxury. I mean, more is better. Yeah, but I'm not afraid, basically, as an embedded system engineer, to work with systems with low memory. Yeah. Yeah. This last one, yeah.
What I really like is that given the constraint, you try to figure out how to solve it, right? I was wondering, like earlier you mentioned about how for one of the features it was like 3 kilobytes.
Yes.
That you had to like not have it, right?
Floating point, yeah.
Yeah, for the floating point feature. Then how were you able to test how much memory has been allocated to task file? Does the Apple II have a feature set to say, oh, this is the X amount of memory taken, you have less memory? How do you like test that?
No, very simple. You just compile with and without the feature. See how much space more
So
extra.
you determine from that. So
Yeah.
your harness test is helping you to.
Yes. So inside my local testing, right, when I build the binary, if the binary exceeds certain size, right, it will alert me already.
So is there a way for you to increase RAM and consider adding that feature set?
Sorry, Ingrid?
Is there a way, like right now since you're playing a lot of the hardware, opportunity for you to embed more RAM into it, then you can consider adding the new feature sets on top of it? Because I would imagine having closures on top of the Apple II is like some pretty cool modern feature set inside.
I'm still limited by the 40K. The extra, the banking, right, you can only load bytecode there. Yeah. So the entire binary still have to fit in. So your closure to pass it still requires the modern RAM. I'm already at the limit already of the main RAM.
So the hardware constraint is not possible to interject any new memory.
There is a way if I switch to assembly code or ask AI directly write the machine code. Then maybe there's a possibility to squeeze out
So
more.
you skip the one of the process.
Skip the C runtime. Yeah.
Thank you.